Hi, I'm Srini Srinivasan from Aerospike. I'm going to be presenting a talk on the paper, Techniques and Efficiencies from Building a Real-Time DBMS. The real-time DBMS we have been working on is called Aerospike. And the first aspect I'd like to speak about is scaling out. Every real-time DBMS today needs to be a distributed system. It's kind of table stakes. And Aerospike is also a distributed database cluster. We use the shared nothing concepts to ensure that we can add nodes with resources to the cluster, and every node is identical. And that's really an important aspect of Aerospike's design. Also, the other aspect is a focus on avoiding hotspots, as well as having smart clients which are able to essentially efficiently access the cluster with one hop without any data, load balancers in the middle. So we do software-based load balancing. We also have dynamic cluster management, as well as the ability to prioritize transactions and long-running tasks in real time. All of this is essentially important to be able to run large workloads without any downtime. Aerospike uses a divide and conquer algorithm. We partition the key space into 4096 partitions. Every key is hashed using RIPEMD 160 to a digest, which is a 20-byte digest, out of which 12 bits are used to provide the partition ID. These partition IDs, therefore, can be up to, are basically 4096 partitions, 0 to 4095 are the IDs, and these partitions are then mapped to nodes. What you see here on the right side is a mapping of these partitions to a 5-node cluster. Depending on the number of replicas, there is some number of columns of this partition map that will be active. Also, the original partition map algorithm that we used for years essentially minimized data migrations. However, that caused certain issues in terms of skew to how partitions were assigned to nodes, which means some nodes got maybe 10 to 15% more partitions than others, resulting in the cluster being limited by the nodes which had the most number of partitions compared to others. In order to make this better, we implemented a uniform partition balance adjustment scheme. So while we were assigning partitions to nodes, when a new partition map is necessary, we would basically adjust the tail end of the partition assignments to make sure that these are balanced across these nodes. And for a non-rack-aware cluster, we can start the balancing maybe 100 partitions before the end, for a 4096 partition assignment. For others, for example, a rack-aware system, we have to start much earlier because the permutations are fewer in terms of where we can assign partitions in a rack-aware cluster. So we have to start it in this particular case for a 100-node cluster, about 1,000 partitions before 4096. Aerospike also supports self-management, as I briefly mentioned earlier. We have various software artifacts which enable us to do this. Detecting nodes, for example, is done by the Heartbeat subsystem. Creating the new cluster is done by the clustering subsystem. But after the clustering subsystem creates a new cluster, there is a new partition map, which is essentially where all the data needs to be after it has been moved around the system from where it is right now, because a node is just added. You see that in the picture on the left. What you have is a node being added to a 3-node cluster, and about 1/12 of the master data and 1/12 of the replica data from each of the existing 3 nodes is basically transferred, dynamically to the new cluster. It takes a while. To the new node. It takes a while for this to happen, but transactions continue as this particular data migration is happening. And the end result of it after migration is shown in the bottom row, which is 1/4 of the master data and 1/4 of the replica data in the cluster stored in every node of the cluster in a 4-node cluster. Scaling up is a particularly important piece of Aerospike. We have worked very heavily on scaling up both on storage, CPU, and network. On the storage side, we have a certain architecture called the hybrid memory architecture. This enables SSDs to be used like memory, so to provide sub-millisecond reads and writes. And this is made possible by the file system algorithm that we have written for SSDs, which is essentially uses the direct SSD device access. It's a highly parallelized algorithm, so you can basically access data in multiple SSDs quite concurrently with high performance. And we also deal with the wear leveling of SSDs using writing through large blocks. We are optimized, for various kinds of SSD like NVMe, PCIe, and so on. We also implement a continuous non-destructive defrag because of the copy and write mechanism results in data being written to a different location. We would have to reclaim data from the old location. This particular algorithm for hybrid memory architecture is much better for large databases, which have to be delivering predictable performance across the entire data set. And this is not something possible with an alternate traditional implementation where you bring data into the page cache and into the essentially the buffer pool in order to read, because then you would have to store the entire database in DRAM, which is prohibitively expensive. Storing all the data in SSD and making them real time is all well and good. However, if you can, which means what happens is from a 100-node cluster, say you can now have a 10-node cluster with each node having 10 times the data, which means it also has 10 times the transaction load. So how do you make that work? For that, we take advantage of the multi-core architectures. We've written the code in C. We have multi-threading. We align the CPUs to the threads. We can do NUMA-based CPU pinning, but also we take advantage of additional advances in networks. For example, Intel released several years ago a network card which basically has supports application device queuing, so we can align the network queue to the CPU and the thread. All of this means that we can pump more transactions per second. For example, without the Intel ADQ setting, we were able to pump about 8.6 million transactions per second in memory through the system, while with the Intel we can pump 15.3. This is all on a single node, and you can see the configuration listed on the slide. Putting together both the scale up and scale out, we can implement distributed transactions a lot more efficiently and provide more availability in a strongly consistent system. So that's what we do by using a roster-based system. We do not use a quorum-based system because our system is fast enough that we can write to all the copies for every time that we have to go to write a record. And that's kind of means that a roster-based system actually works really well for both high performance. We will see also how we can do distributed transactions using the scheme. In this particular example, I want to quickly take you through this. Is a 5-node cluster, and the partition P is the one I'm going to use for illustration. And this partition has the master in node 5 and the replica in node 4. When we say roster, what we mean is when the nodes 1, 2, 3, 4, and 5 here are part of the cluster, that is the roster. Even when the cluster splits, everybody keeps track of the fact that this cluster should have been a cluster with all these 5 nodes. And that information is used to form certain rules. So when a minority subcluster is formed, then everybody knows where the roster replica and roster master for partition P is. In this particular case, nodes 1, 2, and 3 break off. They do not have any of the copies of the partition P, whereas the smaller cluster, the 2-node cluster, has them, and that actually leaves that partition live in that particular cluster for both availability and consistency. And the second thing is, like, there's a different kind of split that can happen. Node 5 can split away, and node 4, which has basically the replica, the roster replica, splits away into the 4-node cluster, which has the nodes 1, 2, 3, and 4. In this particular case, the roster replica gets promoted to master in the majority cluster, and that's where partition P will be active. However, every write to that partition is going to create 2 writes within the cluster, because the replication factor here is 2 for this particular cluster, and 2 writes always have to happen. Otherwise, when the clusters come back together, you will end up with inconsistencies. There are cases where more splits could happen into the system, and we will not be able to maintain availability for partition P anywhere, because consistency overrides availability in this particular setting. Now, these rules are written for a practical purpose. For example, we wanted to make sure that we have 100% availability on a rolling upgrade while maintaining strong consistency, and they ensure that. They also provide 100% availability in case of a 2-way split brain. So all of this, I think, are really important for practically, for running these systems. So the high performance of Aerospike enables us to implement algorithms like the roster-based strong consistency algorithm, and this enables us to provide higher availability during normal network events. Write logic is fairly straightforward. I've already talked about that writes have to be written everywhere. So the client writes to the master, and the master will in parallel write to all the replicas. And when all the replicas are written, master commits the transaction, client gets notified, and then everything moves forward. Now, rack awareness is a very important scheme because this enables us to provide availability in certain kinds of failures. You can see that you have two data centers, essentially, having two racks. Then when one of those racks fails, then the second rack can continue, especially if it has a majority number of nodes in this particular case, as it's illustrated here. However, there are other cases which can be even more sophisticated and available. Here is one example of a case where there is a three-copy system which is distributed across North America. And what you see here is the ability to trade off write latency for a higher availability. So in this particular case, because of the way we write our write synchronously across the entire cluster, we are able to essentially read, however, sub-millisecond, because there is a copy of data available in each of those racks and each of those sites. So this is the trade-offs. You trade off writes, you get reads which are low latency, but you also get strong consistency and immediate consistency, so to speak, across the entire cluster. Now, if a particular rack breaks away in this case, I won't go into that in too much detail, but without operator intervention, the other two racks can continue. And when the rack which broke away from the other two racks comes back and joins, again, without operator intervention, we can continue with no loss of availability or consistency in the portion of the cluster which is live. And that's really important for uptime. Additionally, we also support asynchronous active-active with algorithms for conflict detection and resolution. So you don't have to pay the write latency overhead you pay here. But that is beyond the scope of what I'm discussing here. So I will just show you some performance results based on the work that we have done to give you an idea of the level of impact that this can have in practice. Here is a petabyte scale database, which is compressed to 1/4 size. So the actual data size is 250 terabytes of unique data. In this particular benchmark, 20 i3EN nodes in Amazon. These are fairly large nodes with 768 gigabytes of DRAM and up to 70 plus terabytes of SSDs. You can make all of this SSD data look real time, as I mentioned before. And what you end up with is 250 terabytes of compressed unique user data and 1/2 trillion unique keys. When we pushed a workload in here, we are able to deliver about 5 million reads per second, with 100% of those reads less than 1 millisecond in latency. With an 80-20 read-write load, we're able to deliver 3 million reads per second with 100% latency less than 1 millisecond for the reads, and 754K of writes, which 99% less than a millisecond. So you can see the ability of the system to deliver very high throughput and very low latency is fairly impressive on small cluster sizes. Finally, I'd like you to join our community if you're interested. You can also download various examples and even the code in the community edition if you're so interested in doing more work on this. There's a book. Please join our community if you're interested. Thank you.